So let's apply the knowledge that we have gained till now. Let's pick up a scenario which is close to a real world. We're picking up an infinitely long straight charge wire. A simple scenario, but at the same time, it's not just imaginary. We do see this kind of scenarios, that is to have a straight wire. So we are placing charges on this and we're trying to answer the question of pattern and strength of what? Of electrical field. So what kind of pattern and what is the strength that it will have as and when we move out and we move at a particular angle and so on and so forth. Now, the very first thing that we have to do is we have to talk about Gaussian surface. Once we have that, we have to look at the passing of electrical field lines through the surface. And once we do that, we have to look into the flux. And once we do that, we have to use Gauss's theorem and equate flux to Q by epsilon naught. And this will lead us to getting the value for or expression for E. So the very first question is, what should be the Gaussian surface? Now, the derivation would start like this. We have to describe what kind of charges are we looking at. We're looking at an infinitely long straight wire, right? The straight wire has to be so. If it's bent, then the pattern will be different. With a uniform being that the density or the charge distribution is even throughout, in a very simple language, right? Uniform means the charge distribution, in this case, it's even. Now the question of Gaussian surface. See, Gaussian surface, first thing is we need to look into the pattern of what? Passing of electrical field through the surface, and then we come to a conclusion. Okay, first is, let's look at the pattern of electrical field by this particular structure. So let me show that to you guys, just a second. Okay, let's show this. Now this is your wire, right? And I have picked up a small section of the wire and we are looking at the pattern created by this wire. So how can we justify this pattern? Let me show you guys from a different view. From the cross-sectional view, basically from the top. So the charge, forget about the arrows, look at the charge, look at the wire. It looks like a dot, right? So we're looking at the pattern created by a dot. What is the pattern created by a spherical structure? We have seen this, it's radially outward. So a small section of the wire creates a radially outward structure in this manner. But why is that it's not in any other angle? Why not, in this direction or in this direction? Because the other part of the wire will also be there and they'll cancel each other. We have done enough problem to understand that. You've seen this pattern. So it's always radially outward away from the wire at an angle of 90 degree. It would be so throughout. It would be so throughout. So first we understand the pattern. First we have to understand the pattern. We understood the pattern. It is radially outward. Once we have that question answered, then we have to decide on the surface. What surface is convenient to handle this? So I'll show you guys different surfaces. You guys can decide. First, I'll start with sphere. Again, this is a test. You guys have to answer to yourself. So I'm just showing you guys from all the angles possible. Okay, take pause and have a look. Pause and have a look. Pause and have a look. So that is your sphere, right? I'll do one more thing for you guys. That is to move it. And once more. And one more angle. Now let's look at a cube. zooming out, zooming in, different angles. From the top. Okay, I hope you guys are looking at it with different, by pausing it and all of that. Because in this particular derivation, if we understand things, it'll be a lot convenient to understand any other derivation. That's why I'm going slow. Finally, I have the option 3, cylinder. Zooming out, you can pause. Right side view, top view. And now you guys have to decide which is good. Should we go with a cube or a sphere? Yeah, I hope you guys have decided. It has to be, well, it can't be cube. It should not be cube. It can be cube actually, but it should not be. Can you tell why? See, if I consider this electrical field line, the surface is perpendicular and all of that. So it's quite simple. The dot product will be 1. Cos theta is 1. For this case, cos theta is different. For this case, cos theta will be different. For this case, it will be different, so on and so forth. So it's kind of nice, but it's not so simple. This looks good. Here the cos theta will be equal to 1. This looks like it will be equal to 1, but this looks like it's equal to 1. But when we change the angle, now we'll get to see this. Right? Remember, this is infinitely long wire. So basically, even the top of the sphere will have to encounter electrical field. So when we actually look at this angle, we can see that the electrical field line and the surface will have an angle which is not 90 degree. So it's not convenient. Remember, this is 3-dimension and every point has radiating out, radially outward electrical field lines. So now finally we have a cylinder. Cylinder is your answer. From the top, we can see that this electrical field line is perpendicular. This is perpendicular, 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 so on and so forth. You got the funda. And if the field lines, any other part of the wire is considered, the field lines will always be perpendicular. Because this is nothing but a big fat wire, if you think about it. Is it not? So basically we are taking a structure which is similar to that of a wire. Of course, this need not work out all the time. That is, whatever the structure of the material is, our Gaussian surface is also a bigger, fatter version of it. It not be the case. Okay, guys. So the surface here is a cylinder. That's it. If you are able to understand Gaussian surface, you are pretty much done. Right? Please rewind. Please look at the section of the video because this is important. I'm not going to repeat the Gaussian surface aspect anytime in the future. So electrical field line generated by the line charge is radiating outward. The word radiating should not be missed. And with the same magnitude at all points equidistant from the wire. Hence, we can have a cylindrical Gaussian surface to study the electrical field. And we are considering this to be of radius r and length L. So to figure out the flux, next thing is flux once we are done with the Gaussian surface. So first thing is, actually I should be drawing the Gaussian surface. That's a wire. So a rough diagram is good enough. This is your imaginary, right? And this has a charge density of lambda coulomb per meter. This has a radius of r and this has a length of L. It's the Gaussian surface. The wire itself is infinitely long. Okay, guys. Right? Now, how many surfaces can we break this structure into? A flat surface at the top, a flat surface at the bottom, right? So we can call this as S1, this is S2, and the curved surface area, S3. Now let's consider a small section of all of this, S1, S2, and S3. I can do this. So sensibly, we can divide the structure of entire surface into three different surfaces: top, bottom, and the curved surface. Agree? And next step is we're considering three small section of, right? Three small section, one from each. And now we look at the electrical field line going through them. The field line for this would be in this manner. The field line for this would be, say, in this manner, right? And for this, it would be in this manner. Now let's look at the area vector for each. So this would be perpendicular to this. This would be perpendicular to this, and this would be parallel to this. So remember, this is your E, E, and E, and this is your DS3, DS1, and DS2. What does DS mean? A small section of the surface. So what can we tell? Clearly, field lines is perpendicular to the entire surface element of S1 and S2, while it's parallel to S3. Therefore, theta S1 is equal to theta S2, which is equal to 90 degree, and theta S3 will be equal to 0 degree. Right? So this is all the conclusion that we can come to. Next, let's look at the flux. So electrical flux is surface integral of EDS. Now, the entire surface we are divided into three parts: S1, S2, and S3. Agree? Is it not, guys? So just we have to take the dot product between all of them. Again, see, it's so structured. You guys don't have to even think too much. Now, this will be 0 because theta is 0, theta S1 is 0. I mean 90 degree, 90 degree. And here we'll end up with integration of E S3 cos of 0, which is equal to 1. Right? So we can give the reason it's from 1. The electrical field lines are constant throughout, right, through the surface, so that will come out. We just have to integrate this surface. That is basically, what is the entire surface? The entire surface is nothing but 2 pi RL, curved surface area of a cylinder. Okay guys, this is curved surface area of a CSA of a cylinder. So next part, the electrical flux is also given by Q by epsilon naught, right? This is as per Gauss theorem. and the charge density is lambda. Therefore, Q is equal to lambda L. That is the charge enclosed. Again, we're talking about Gaussian surface by the Gaussian surface. Does it make sense? What we're trying to tell here is this length is L and this has a density of lambda. So density into the length will give us the charge within that space. So from here till here, the charge is lambda L, right? Therefore, on substituting, what we end up with is equal to lambda L by epsilon naught. So from 3 and say 2. 1 and 2 both are equal to electrical flux. So E 2 pi RL is equal to lambda L by epsilon naught. So here L and L will get cancelled and E is equal to 1 by 2 pi epsilon naught times of lambda by R. So many Newton per Coulomb. So what can you conclude from this? That the electrical field lines are inversely proportional to the radius. Electrical field lines are inversely proportional to the, not radius, sorry, length. It's not square, it is linear. That's important. But if a single charge, the decrease is at a rate of inverse square law. But here it is not so. Right? Does it make sense? Because it's r to the power of 1. It's as simple as that. So guys, here the main funda is to understand that we can derive a very complicated scenario using Gaussian theorem and surface and so on and so forth. So very first thing is choosing the Gaussian surface. For that we need to know the pattern of electrical field line produced by that structure. Once we know that, we can choose a surface by choosing a surface in a way that it's either perpendicular, parallel, or in a particular angle, so that we can put a general rule to the entire structure or part of structures. 4-5 structure, 4-5 surfaces has different angles that can be handled. But each of them having different angles, to be honest, even that can be handled, but it's not convenient. So we have taken up a surface which is very convenient. That's a cylinder. And with respect to surface 1, 2, 3, again we have to check out the electrical field lines coming out of it, right? Because we can make use of Gaussian theorem, which tells that the flux through any structure will be equal to the charge that it encloses divided by the proportionality constant. So using that, we have derived this entire result. Now pause, have a look, and copy it, of course.